Oh, study on a virtual prototyping-based design verification methodology. Abstract. Certainly, design complexity and size of SoC is increasing exponential. However, design team is increasing the contrary. To reduce the verification time, the complicated SoC and improve the verification quality. This paper proposed a new verification methodology using the co-simulation technique of SystemC models on virtual prototype VP and Verilog RTL register trans-level model. Furthermore, in the proposed methodology, software-based test cases developed through VP, virtual prototype, can be reused in RTL, design verification, and software validation. These test case reuse minimizes the verification planning time for each verification stage and enables the regression test from the beginning of IP, intellectual property design. Through this, it is possible to secure design quality early. Through the proposed verification methodology, not only functional verification, but also specification verification can be performed at the same time. Therefore, design time increasing can be minimized by preventing design errors based on the same criteria for each design stage. In order to apply the proposed methodology into real SoC system-on-a-chip project, there may be a time overhead for developing a SystemC model for all IPs. However, since VP is already being used for early software development and performance estimation, many IPS models were already developed, so the proposed verification methodology can show maximized TAT turnaround time, reduction effect without a time override for model development in real SoC project. As a result, design verification time is reduced by 20%. Through test case reuse, verification planning time was minimized, and regression could be started a month early by adopting VP co-simulation. Introduction. As a design complexity increases as SoC architecture exploration or a specification verification becomes more common process. To meet the customer's demand, it's been necessary to find optimal architecture by architecture exploration. Find optimal architecture by architecture exploration and to check whether the design specification is properly established or not. Furthermore, ESL, electronics semiconductor level, based VP, virtual prototyping, is often performed to estimate functionality, performance, and power consumption early. Moreover, in automotive product, VP for software development becomes essential process to develop the software in advance and secure safety early. VP can be used for various verification platforms by using traffic generators, software, and direct SFR, special function register. Control from the test vectors used in RTL verifications. Test cases can be described as various languages such as System Verilog C, C++, SystemC, and so on. These are used easily at the verification of each RTL, FPGA, and silicon stage. Test cases in various languages are run on the SoC level simple OS and are configured as SFR sequences of hardware or described and used as higher level functions along with the device drivers and simple OS. In addition, in order to use the same verification cases at each stage, the items for verification are managed from the IP design stage, and the verification results are version controlled with the RTL models. Test case reuse not only reduced the test case description time because redundant activities can be avoided at each stage of verification, but also it guarantees the verification quality each stage of the development at the same level. It can be said the method or direction is the same as the portable stimulus standard PSS. The test cases can be modified or added at verification each stage, but in most cases, those are able to be reused without any modification, which is effective in reducing the time to write the test case. In this study, the SystemC model and the verification developed for architecture exploration were applied to RTL verification, and a technical exploration for proposed algorithms will be introduced in the following chapters. 2. Related works. The virtual prototyping. Through high-level programming languages such as SystemC or SystemC or C++, the behavior of the structure of the IP can be modeled the same as the real design. Thereby, the building a virtual SoC or system. Such a virtual system is called a virtual platform and can develop and verify the hardware or software operation of the virtual platform. All of these activities are called virtual prototyping. When IP models is performed using SystemC, it is possible to make a difference in function and timing accuracy and model operation speed according to the description precision. In order to verify the design and estimate performance or power consumption, the cycle accurate model for the approximately timed model, which is known to have a timing accuracy of around 90%, is generally used. These models have an operation speed of several kilohertz to several megahertz. For software development, the operating speed of the model is very important, and the usually timed model with a 70 or 80% timing accuracy or a function accurate model that considers only the sequence without a timing information is generally used. The operating speed of this model is several megahertz to several hundred megahertz, which is widely used for early software development or software regression testing in automotive SoC project. In fact, many semiconductor companies are using VP from the beginning of the project to perform architecture exploration based on hardware performance and hardware estimation, and to complete the software development before the silicon releasing. B. SystemC-RTL code simulation. The hardware model described by the SystemC and hardware model described by the Verilog have the same specification, but the languages describe the behavior and the structure are different. The Verilog model has signal level interfaces, and the SystemC models has a signal level or a transaction level interfaces. If a signal level interfaces are used in the modeling, those can be connected without a special connecting models and can be simulated with the same clock scheme. In case of SystemC models with the TLM transaction level modeling interfaces, those can be easily connected through the transactors. Those can convert transaction level to signal level. In general, UVM, the universal verification methodology widely used for RTL verification, consists of TLM interfaces, and the transaction conversion between the TLM and signal is easy. For this reason, SystemC or RTL simulator basically provides the code simulation feature. A typical SystemC and RTL code simulator consists of the DUT, design under test, consisting of the Verilog RTL and a test bench composed of the SystemC. Simulation is often performed by transmitting the test sequence defined in the SystemC to the DUT and I/O through the DPI direct programming interface core. In this paper, the DUT consists of both the SystemC and RTL, and the test bench is written in SystemC. In some cases, SystemC models can include its own simulator. To run both RTL simulator and SystemC simulator, one of them shall be master and the other shall be a slave. By the reason, each simulator must support both master mode and slave mode, but it is common not to support the slave mode. To solve this problem, it is necessary to use a custom-made DPI core or a custom wrapper. Alternatively, an old version of the simulator may be used. C. Portable Test and Stimulus Standard, PSS. In order to increase verification productivity, the use of the verification intent is required from IP level design to a silicon level chip design stage. The concept of PSS is only to describe test intent and behavior once and target it multiple abstraction layers such as IP, block, and SoC. This includes the verification platforms simulation and emulation silicon. These platforms have separated requirements and use different languages, as well as different approaches when testing aspecting of the system. PSS supports random and non-random data field and structure that are familiar with the system Verilog. From object-oriented programming, they support familiar inheritance patterns. Figure 1 shows a presentation of the autonomy of PSS, how one goes from a PSS description to executable code. 3. The proposed methodology. A. Proposed design flow. This paper proposed a verification methodology which uses VP for a hardware architectural exploration, and as the RTL design progressed, a method for verifying the function while replacing the SystemC model with the Verilog model was proposed. Figure 2 shows the overall features of the proposed methodology. The Figure 2, the proposed verification methodology. SystemC model development time is faster than the Verilog model development time, and the modeling is started during the architecting. It can be used secured at the early design stage. The test cases for SystemC model functional verification can be described and be simulated using software or SFR sequences to RTL simulation, and the test cases are combined and used for regression test. When the design starts, IP is developed sequentially and delivered to the block or the SoC development team. As shown in Figure 2, the SystemC model is replaced with the Verilog model, and then the verification is performed with the same test cases. Finally, when all IPs are replaced with the Verilog models, it is the same as the existing RTL verification environment. Since the regression test is possible whenever each IP is replaced, the regression test can be started earlier than existing RTL verification method. Therefore, the root cause of the error can be specified as replaced IP and debugged quickly. In general, the SystemC models created for early software development many differ functional and structurally from the actual RTL models. For this reason, even if the test cases are run, all functions defined in the RTL may not be verified in SystemC models. However, in this study, when developing the SystemC models, the behavior and the structure were developed as same as the actual RTL design. This development method also requires systematic collaboration between teams so that all related teams can use the same. SystemC-RTL transition. There are various methods in the signal transition between the SystemC model and the Verilog model. The Verilog model of the RTL is used to cycle-driven and a signal-level transition. Assume the signal transmitted at each cycle. On the other hand, the SystemC model have a flexible interface structure. Signal-level interface can be used, and the TLM interfaces can be used for a faster model operation. Figure 3 shows the difference between the signal-level transition and the TLM for read or write for AMBA, Advanced Microcontroller Bus Architecture from ARM, AXI, AMBA, AXI. The Figure 3 format comparison between signal and TLM. For SystemC models for performance estimation, cycle-accurate model is used to to calculate the timing accurately even if the model operation speed is low. And in addition, in order to ensure the operation speed of software development, usually timed TLM models which have slightly lower timing accuracy but a faster operation speed and uses the only sequence orders. Is widely used. In this paper, both model and developed for performance estimation and a model made for early software development were used. The transactor between the signal level interfaces of Verilog models and the TLM interface of the SystemC models were developed together. Figure 4 shows the structure of the transactor used for RTL signal, RTL system C, and co-simulation in this paper. The TLM transaction data is separated into each AXI channel, and each signal in the channel through the FSM final state machine, and the signals are transmitted through the radiant valid handshaking. Conversely, the signals are translated and converted into TLM package through the FSM and transmitted to the TLM interfaces. But proposed transactor transmit data at cycle 0 and was written in by SystemC or C++. Figure 4, the TLM signal conversion scheme. The C model structure. In order to apply the simulation flow proposed in this paper, the same behavior and the structure between the Verilog model and the SystemC model must be maintained. Also, it is necessary to have the same functionality, hierarchy, and interfaces. In this paper, SystemC model was made to include the prefers used in SoC based on RTL design, hierarchies, and functionality, although simplified than the real RTL design. And the same operation can be guaranteed based on the SFR controller. Behaviors of the IP are described first, and the behavior or function model is wrapped by the SFR wrapper over them. In the case of SFR wrappers for each IP, a generator for parsing the SFR sheet was developed in this study. Figure 5 shows the structure of each IP, and the SystemC IP model is integrated into the Verilog top for co-simulation. A register information signal driver was developed for SFR communication with the Verilog models, and the interface used to correct some differences in hierarchy and to convert the protocol. In Figure 5, the interface is shown as separated from the transactor to explain the function easily. But in the real implementation, the interfaces are included each transactor as shown in Figure 4. In Figure 5, transactor architecture. 4. Experimental result. In this paper, the proposed verification method was applied to a 100 mega gigacount mobile flagship AP SoC to be confirmed. The proposed verification methodology was applied to the bus clock and memory controller block, which are the most important for SoC performance. The bus block developed the SystemC model for 12 IPs, and the memory controller developed the SystemC model for 7 IPs. A comparison was performed about the simulation speed and the verification period for the proposed co-simulation method. The results of the experiment are shown in the Table 1 and Table 2 as below. Table 1, the result of simulation speed comparison. Table 2, the result of verification period reduction. The existing verification method and proposed method were compared using the same number of test cases. According to the simulation speed comparison result in Table 1, SystemC-only simulation was 5.22 times faster the average than RTL-only simulation, and the co-simulation was 1.16 times faster the average than the RTL-only simulation. In the case of co-simulation, the speed may vary depending on the various variables as well as the number and volume of the RTL models. And so the speed was measured whenever RTL models were included in the average speed of them was used for a comparison. As shown in the table 2, it was confirmed that the verification period was reduced by 21%. It's based on the verification completion date of the SoC from the start of the verification IP and block, and does not include the silicon validation period. Since the first RTL was released, a regression test for IP and block could be started, and the verification began quickly, allowing bug finding and debugging from the earlier stage of the project. By the region, debugging activities decreased during the SoC verification period or in the second half of the project. In the end, it seems that the verification completion date had been pulled in. According to the real design verification flow, the verification scenario for each design stage is being developed in parallel. Verification planning and the test case develop time reduction did not appear during the entire verification period, but it is expected that there will be benefit in terms of human resource reduction. 5. Conclusion. In this paper, a design verification methodology using VP virtual prototyping was proposed. By applying the proposed methodology, the functional verification of each IP could be performed more quickly at the block level, and the regression test was started quickly for more than a month, and the same level of verification quality was secured during the verification period, which was reduced by 21% on average. In order to apply the proposed methodology in this study, SystemC modeling tasks for IP are required, which can be an overhead for resources such as human and time. For this region, it may seem difficult to apply the proposed methodology. However, most semiconductor companies already use the functional models for design widely, and many of them already use the model-based design methodologies for all software development, architecture development, performance, and power estimation. This allows the resources overhead to be hidden. Moreover, virtual prototyping is essential for the recently popular software-driven hardware development methodology, and is seen as a good methodology to create a synergy. The verification methodology proposed in this study was applied to the specification and functional verification first, but it is expected that these kind of verification can be performed quickly and easily by utilizing the performance and power estimation flow described above. Okay, thank you for your time. I read the DVCON2023 paper, a study on virtual prototyping based on design verification methodology. Thank you again. See you next time.